Section 6.2, we're looking at covalent bonding and molecular compounds. First of all, looking at what a molecule is. So a lot of times people get molecules and compounds confused, but basically the difference is the type of bond that holds that together. So for a covalent bond, that's going to be a molecule. So we've got a couple of molecules shown below. So a molecular compound is the simplest units that make up a molecule. So here we're looking at chemical formula, which should be familiar to most of you. Just to kind of clarify and make sure we're all on the same page, you're going to have your symbols for the elements, making sure that you use capitals where the letters are supposed to be capitals and lowercase when they are supposed to be lowercase. If we were to use improper capitalization or lowercase, sometimes that's going to give us different elements. So if I have capital C, little o, that's cobalt. But if I have capital C, capital O, that's copper and oxygen. So be very, very careful because you will miss points if you do not write those correctly. Also, here we've got Na2. That 2 tells me how many sodiums I have. When we don't have a number in chemistry, that's understood to be a 1. So here we would have 2 sodiums, 1 sulfur, and 4 oxygens. When we're looking at molecular formulas, that's going to show the simplest ratio of the elements that we would need to make that molecule. And so here we have to have 6 carbons, 12 hydrogens, and 6 oxygens to make a glucose molecule. Now, the smallest ratio would be carbon, 2 hydrogens, and 1 oxygen, but that's not going to make glucose. So the 6, 12, 6 is what we have to make a full glucose molecule. Diatomic molecules are molecules where you have an atom that has to be paired up with itself to exist. And so these are going to be important later when we're writing chemical reactions. If you don't know that something's supposed to be a diatomic molecule, then you're going to miss your reaction. So those elements that are diatomic are hydrogen, nitrogen, oxygen, and group 17. So you can see here oxygen, when it's by itself out in nature, it's going to be in a pair, so O2. Same thing with nitrogen, N2. So make sure that you remember it's hydrogen, nitrogen, oxygen, and group 17. So if we have a reaction and you're told you have oxygen combining with water to make something, you would have to write that as O2 plus H2O produces whatever. So looking at some characteristics, first of all, we have to look at bond length. So we're just looking at how long is the bond between 2 atoms. And the lengths can vary depending on how badly things want electrons, the size of the atoms, many different things. Bond energy is going to be the energy required to break those bonds. And so it's going to be different depending on the length of the bond or if we have multiple bonds holding atoms together. One thing to try to remember, the longer bonds are going to be easier to break. They're going to require less energy. And so I think of this in terms of a pencil. If I have a long pencil, that's a lot easier to break than a little short pencil. So this is a chart of different bond lengths and the energy required to break those. So you can see shorter is going to require a little bit more energy. Then if we're going to have multiple bonds holding things, those require more energy to break rather than just a single bond. The octet rule we've looked at a little bit, but this is just looking at the fact that elements want to have 8 electrons in their outer shell. And so they're going to do whatever it takes to get those 8 electrons, whether it's gaining, losing, sharing electrons. They're going to do whatever it takes to satisfy that octet rule. There are a few exceptions. Hydrogen and helium, which we've discussed, those only want 2 because they only have an s orbital to fill. Boron typically wants 6, and there are a few more, but for the most part, we're going to just stick with the rule 8 or hydrogen and helium 2. Then we're going to look at what's called the electron dot notation. So with the electron dot notation, this is going to show the valence electrons that an atom would have by putting the symbol of that element in the middle, and then its valence electrons are represented by dots that would be then placed around that atom. So hydrogen has 1, so it would have 1 dot. Fluorine has 7 valence electrons, so it has 7 dots around it. So this is, again, looking at that fluorine. And so we're going to typically space them apart. So 2 on bottom, 2 on top, and then 2 on each side if that's how many we would have. When we are looking at bonding atoms together, we're typically going to place them where they're sharing those dots. So if we look here, hydrogen, carbon, they are both able to count those 2 dots towards their 8 or 2, whatever they need. Sometimes we have dots that aren't shared between atoms. So for example, these aren't shared with another atom here, so those are considered unshared pairs, or sometimes they're called lone pairs. So a Lewis structure is going to show you how atoms bond based on their valence electrons. So this would be the Lewis structure for water. So one thing that we'll look at, if we have oxygen, which if we were to look at the valence electrons for oxygen, it's in group 16, so it has 6 valence electrons. So it would bring 1, 2, 3, 4, 5, 6, and each hydrogen brings 1. But when they're combined, oxygen can count a total of 8, and each hydrogen can count a total of 2, so they all have that satisfied outer shell. The next thing to look at here would be a structural formula. With structural formulas, or even Lewis structures, when you have a line, this is representing 2 electrons. A structural formula is just showing you how the atoms are bonded together without all of the unshared pairs. But keep in mind, a line means 2 electrons and a dot means 1. So here we're seeing single bonds. So a single line between 2 atoms, and then we have another single line. So we can say 2, 4, 6, 8 electrons around carbon to satisfy that 8. Each hydrogen has 2 next to it, so they are satisfied as well. We can have multiple bonds between atoms. So here, carbon and this top oxygen have 2 lines, which means they're sharing a total of 4 electrons. And we can even have triple bonds. So if something were to have 3 lines, they would be sharing 6 electrons. Some molecules can bond with the same atoms, but just in different ways. And those are called resonance structures. So here we've got a double bond between this oxygen, where on the other structure, it's double bonded to this oxygen versus this one. So just different ways to make the same structure. And so this is looking at it with O3. So we've got the double bond on one side versus the other. In this next section, we're going to look at what's called electron dot notation and how to write those. So first of all, we're going to be writing Lewis structures. And the first thing we're going to do is we'll be given a formula, and we're going to find the total number of valence electrons for the molecule that's given. We're going to connect each of the atoms with a pair of electrons or a line representing 2 dots. And then we're going to fill in the rest of the dots around the molecules, around the atoms, so that all of the atoms have 2 electrons unless it's hydrogen and helium. and those will have 2. And then we're going to make sure that we have used the total number of electrons that we calculated in step 1. So here we're going to start with CH4. So the first thing we need to do is figure out how many total electrons CH4 would have. And we're going to use the valence electrons. So if we look at our periodic table, carbon has 4 because it's in group 14, and hydrogen has 1 because it is in group 1. So we'll make a running total. So 4 for carbon plus 1 for hydrogen, but we have 4 hydrogens. So this gives us a total of 8 electrons. And so when we finish, we will have had to have used 8 total electrons. The next thing we want to do is we want to connect all the atoms. So typically, the first atom you're given, you're going to put in the middle. So we've got carbon. And then everything else is going to go around carbon. We cannot put hydrogen and helium in the middle because they only want 2. So we've got carbon in the middle. We're going to put hydrogens on each side because we have 4 hydrogens. So now if we look at this, carbon has 2, 4, 6, 8 electrons total, and each hydrogen has 2, which is what they need to each have. So we've used our electrons. We've given everything the total number of electrons that they need to have a full outer shell. Let me get rid of these extra colors here. And then we have one more thing we have to check. So we have to go back and look at our total number of electrons. So in our molecule here, did we use 8 total electrons? Which we did. We've got 2, 4, 6, 8 that we've used. So our molecule would be done. So for the correct answer, you would just have this structure. Let's try another. The next one here, we have BF3. So if we check our periodic table, B has 3 valence electrons, F has 7. So B has 3 plus F, which has 7, but we have 3 Fs. So our total is going to be 24 electrons that we have to use. So first, we're going to put B in the middle. We have 3 Fs to put on each side. So at this point, we have used all the atoms in our molecule. The next step is to put dots around everything so that each atom has a total of 8. So right now, B has 6 because we've got 3 lines. So we'll put 2 dots on top. So the boron has 8 around it. Each F has 2. So we need to make sure each F has 8. So 2, 4, 6, 8. And now the bottom F, 2, 4, 6, 8. And then the last F, 2, 4, 6, 8. So at this point, everything has 8 electrons around it. And now the last step is making sure that we have only used 24 electrons because that's the total number that we were looking for. So I'm going to use red to count. But right now, we've got the structure that we think we need. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We cannot use 26 because we did not have 26 to start with. So what can we do? So let's redraw that. here's what we're starting out with. So at that point, we've got 26. We only need 24. So what we're going to do is we're going to pick one of our fluorines. And we're going to take 2 dots off of that, which there we'd have 24. But the fluorine doesn't have 8, so that would not be correct either. So then we're going to take 2 dots off of the boron, and we're going to make a double bond between those. So now the boron still has 8, all of the fluorines still have 8, and if we were to count up our total, now we're going to have 24. So this would be the list structure for BF3. How about HCN? Look at your periodic table. Hydrogen has 1 valence electron. Carbon has 4. And nitrogen has 5. And if you're not sure where we're getting these numbers, make sure you ask, because this is important that you know how to do this. So at this point, we're going to add that up. And we have a total of 10. So for our 10, we're going to start out. Remember, we can't put hydrogen in the middle, because if we were to put hydrogen in the middle and then we combine our atoms, it's already got 4 around it, and it can only have 2. So we'll put carbon in the middle, connect our other 2 atoms. So hydrogen has the 2 that it needs. Carbon needs filled up, so it has 8. And nitrogen also needs filled up, so that it has 8. So at this point, we've got 8, 10, 12, 14 total electrons. So we're going to do some double bonding. So we'll take those off, put a double bond. So we've got 8, 10, 12 at this point. So we're going to need to make a triple bond. Carbon has 8, nitrogen has 8, and we've used 10 electrons. So this one would be complete. How about NH3? Nitrogen has 5. Hydrogen has 1, and there are 3 of those. So we need 8. So nitrogen in the middle. We'll put our 3 hydrogens around. The hydrogens are all good because they have 2. We'll add 2 dots to nitrogen to give it the total 8 that it needs. The whole molecule has 8, and that's what we're looking for, so this one's complete. Let's look at one. Here we go. Cl O3 with a negative. So that negative is something new. So if we go ahead and start our totaling our electrons, chlorine has 7. Oxygen has 6, and there's 3 oxygens. Now, when we have a negative charge like that, that means that we have added electrons. So if it's negative, that means -1. If it says -2, maybe it's a plus sign, which means we've gotten rid of electrons. So whatever that sign tells us, we're going to do the opposite. So it says -1, so we're going to add 1 to our total of electrons. So we've got, excuse me, we've got 6 for oxygen, and there are 3 of those. And then we're going to add the 7 and the 1, which gives us a total of 26. Chlorine in the middle, 3 oxygens around. Fill everything up with 8. If we total this up, we've used our 26 and we're done.
So remember to watch for the signs, positives and negatives, and add or subtract that to your total number of electrons.